Alright, what's up guys? In this video we're going to pick up some vector calculus and we're going to evaluate another line integral here. So we're asked to evaluate this line integral y sine of z ds, where c is the circular helix given by the following parametric equations: x is equal to cosine t, y is equal to sine t, and z is equal to t, where t is between 0 and 2 pi. So really all we have to do here is just use the definition for the line integral in R3. Okay, and there's two ways that your textbook may write it, and I'll write it both ways because I like to specify. So if we have our line integral f ds, that's just going to be equal to the integral from a to b, and it's just going to be f of x of t, comma y of t, comma z of t, multiplied by the magnitude or the norm of r prime of t dt. That's the first way it's written. The next way it's written, which is exactly the exact same thing, except it's just written differently, is f ds is equal to the integral from a to b. It's going to be f of x of t, comma y of t, comma z of t, multiplied by the square root of dx over dt squared plus dy over dt squared plus dz over dt squared dt. So I always like to make sure that I write them both out. These formulas are exactly the same thing. Again, some professors may use one of them, some professors may use the other, and sometimes it can get a little bit confusing for students in math if different formulas are used that are really saying the same thing, but some professors, maybe you're not used to using a particular formula a certain type of way. So I always like to specify the two different ways that you may see some things written. Now, we've evaluated plenty of line integrals before, especially scalar line integrals and things like that. So in my videos, you guys will probably already know what most of this is, but I do like to specify just right off the rip. So pretty much all of the work is kind of done for us. I mean, they give us the parametric equations. A lot of times with these line integrals, we have to go ahead and parameterize the line segment and stuff like that. In this particular case, they already give us pretty much everything. We already given the parametric equations, so it's really just a plug and chug process, and then we just got to evaluate the integral. All line integrals won't be that easy, so don't get too stuck on that. But in this particular case, they already give us all of our information. So all we need to do is just really go ahead and just set this thing up, simplify it as much as possible, and then evaluate the integral. So we got y times sine of z, and it's going to be ds. The limits of integration here are going to be from 0 to 2 pi. And it's just a substitution process at this point. So it looks like we'll get sine of t multiplied by another sine of t. This will be times the square root, and we'll take our derivatives. Won't write that down, we'll kind of just do it on the fly here. So we'll need dx over dt. That's going to be minus sine of t squared. We need dy over dt, which is cosine of t squared. And then we need dz dt, which is 1 squared, and that's going to be dt. And we continue with the simplification, so it's going to be from 0 to 2 pi. This becomes sine squared of t. Okay. When we simplify, in this particular case, what we're going to end up getting is the square root of sine squared of t plus cosine squared of t plus 1 dt. Now recall that sine squared of t plus cosine squared of t is equal to 1. So that means that we'll essentially have the square root of 2, which is just a constant, it's just a number, which we can pull out front. And we can use a half angle identity to rewrite sine squared of t, and we'll evaluate the integral from 0 to 2 pi. So as you can see here, nothing really crazy going on here. So let's go ahead and rewrite this a little bit. So from 0 to 2 pi, and we're going to use a half angle identity here. So this is just going to be 1/2 times 1 minus cosine of 2t multiplied by the square root of 2 dt. Now I'm going to pull the constants out, but I did want to just leave them in there for a second just to show you what was done. Okay, so hopefully everything makes sense so far. All right, so let's finish this integral up. Okay, so I'm going to pull out the 1/2, and I'm going to pull out the square root of 2. I'm going to have to keep looking back because I need to be able to see what we got. And then the integral is going to be from 0 to 2 pi, of course. And we need to evaluate 1 minus cosine of 2t dt. So again, nothing crazy going on here. If you want to simplify the constants on the outside right off the bat, you could certainly do that. You don't have to. You can wait to the end to simplify the constants. As long as you're doing it, don't forget that you pull the constants out. But some people go ahead and just take care of the simplification and multiply the constants out at the beginning. Some people wait to the end. It really doesn't make a difference as long as you do it. I guess I'm going to go ahead and do it here. So if I simplify the constants out here, I'll just get 1 over the square root of 2. And again, we'll just go ahead and take care of all this stuff right now. So notice how I'm going through meticulously every single step, not skipping anything, because I want you guys to understand what's being done. I don't want to assume everybody knows what's going on. So now we'll break this integral up here a little bit. So this 1 over the square root of 2 that we have on the outside, okay, no big deal. So we'll break it up. So from 0 to 2 pi, we'll be integrating 1 with respect to t, and then we'll subtract that from the integral from 0 to 2 pi, and then we have cosine of 2t dt that's going to evaluate. So let's deal with that. So again, these are small little steps that you do not have to write. Again, for the purposes of the video, I'm going through all of these meticulous steps. But if you're doing this at an actual class, all these small little steps I'm writing down, at least by the time you get to vector calculus, you should easily be able to calculate most of these integrals without even have to write down a bunch of stuff. But I'm just writing down all the steps for the purposes of the video, so bear with me on that. So clearly, all I'm going to get here when I evaluate this integral is just going to be 2 pi, because when we sub in 0, we get 0. Now let's move on to the next one. So from 0 to 2 pi, we need to integrate cosine of 2t dt. That's what we need to take care of. Now remember the antiderivative for that. That's just going to be 1/2 sine of 2t. But we need to evaluate it from 0 to 2 pi. Okay. So we need to stick in this 2 pi. We also need to stick in the 0. Now we're going to get 0 when we stick in 2 pi. We're also going to get 0 when we stick in the 0, because sine of 0 is 0. So 1/2 times 0 is 0. So we're also going to get 0 for that. So obviously that just is 0. So now we take our 1 over the square root of 2, and we'll multiply that by 2 pi. And then we're going to subtract that away from 0. And then that's just going to end up giving us the square root of 2 pi after we simplify it, which would be your final answer. So your final answer for this line integral is going to be square root of 2 pi. Alright, that's your solution. Okay, so let me circle that for you. And that's your answer. So just another line integral in space here, but went through all the steps meticulously, and so hopefully you were able to get an understanding of everything that was being done. Alright, so that's going to be it for this video. And let me know if you have any questions. I'll see y'all next time.